Alright, so you have to do the gas lab calculations. Here's the way it works. First of all, the objectives for the lab, we wanted to do two things. Based on our experiments, we wanted to be able to determine the value of the gas constant R. The other thing is we wanted to determine the volume of 1 mole of gas at STP, standard temperature and pressure. Remember R, the ideal gas constant when we did the gases, is 0.0821 rounded off, and there are the units for R. So what do we need to do? Well, the first thing we did in the lab is we took magnesium, we reacted with hydrochloric acid, produced MgCl2 and hydrogen gas. The hydrogen gas is what we caught in the tube and measured, and those things will allow us to do the two calculations, gas constant R and the molar volume of a gas at STP. So if you follow along with your data, stop the video when you need to do your calculations. You should be able to complete the lab in no time at all. Now, first thing you have to do is calculate moles of gas. So you guys measured out some moles. I'm making up a fake number here. So let's say I had 2.5 grams of magnesium. I need to convert it into basically amount of H2 gas produced. I go back to the equation right here. I'll use this equation. So if I have 2.5 grams of magnesium, molar mass of magnesium would be 24.3 grams of magnesium is equal to 1 mole of magnesium. Finally, the ratio of magnesium to H2 gas is 1 to 1, so 1 mole of Mg is equal to 1 mole of H2. That will allow us to calculate moles of H2. Now, obviously you didn't start with that same number of grams of magnesium, but you plug it in. You should do the stoichiometry. You should remember that from chapter 3. So moles of H2 gas is very easy. Take the mass of the magnesium ribbon, which you should have in your data table, do the calculations like you saw right there. In the end, you'll end up with moles of magnesium. So that's calculation 1. So you should label it with the title moles of H2 gas, set it up, and show everything. Second thing you have to do is you have to basically find the pressure of your H2 gas. Remember the day we did the lab, barometric pressure, you had to write it down, I think it was 30.10 inches of mercury. Well, I'll tell you the conversion is 29.92 inches of mercury is equal to 760 mmHg of mercury. So the first thing you're going to have to do is convert it to millimeters of mercury. So what you would do is you would draw a grid, plug in your value, and I'm not sure that's the exact value. You plug in your value from the lab, and you would put... So then what you do is you place the 30.10 inches of mercury or whatever it was that day when we did the experiment. You had to write it down in your lab. You'd put 29.92 inches of mercury. Hg is equal to 760 millimeters of mercury. So then in the end, the answer that you will get will be your volume of both water and hydrogen gas that was in the tube, because remember we collected above water, which brings us to this part. You measured the temperature of your water. Remember when we talked about the temperature of a dry gas and collecting a dry gas, the total pressure, you have to change it to the pressure of what was inside the tube, or the pressure inside there, is equal to the pressure of water plus the pressure of hydrogen. We just care about the pressure of hydrogen. So what do we have to be able to do is we basically use the total pressure, whatever it comes out to be. So you convert it using this one, whatever your answer is here. Whatever your answer is here after you do this grid, you're going to take that and you're going to come down to the chart. Let's say hypothetically your temperature of your water was 28 degrees Celsius. You're going to subtract 28.3 millimeters of mercury from that, because that's the pressure of water at that given temperature. The pressure of water vapor at a given temperature is based on this table. So let's say hypothetically the last calculation I converted it and I had 730 millimeters of mercury. I'm just making up a number here. And I collected it at, that would be my total pressure. That's going to be equal to my pressure of hydrogen gas, which is what I really need, plus water. If it was at 28 degrees Celsius, then the pressure from that would be 28.3 mmHg. So then all I would have to do is algebraically solve for H2 gas. So I'd take 730 minus 28.3, and I would end up with 701.7 would be my pressure in millimeters of mercury of my H2 gas. And that's what you have to do, because we want to isolate just the hydrogen gas. Whenever you collect anything over water, you're going to have the water vapor there. So that was the whole point of taking the temperature, was we found the temperature of the gas, but we could also take out the water vapor, because since we collected over water, there will be water vapor there. So that's step two. Step two is to take the pressure of H2 gas. You did your conversion before you even started. You would use this setup right here. Take the value of the temperature, whatever temperature your reaction occurred at, probably 24 or 25. One of these values, you would use one of these values to basically take the total pressure minus the pressure of water will give you the pressure of hydrogen gas. Then we go over here. Volume of hydrogen gas is very easy. You measured it. This is just taking the value from your lab sheet milliliters, changing it to liters. That's a simple metric conversion. You would show that though. Show the setup and do it. Temperature of the hydrogen gas, very simple, is you measured the temperature in Celsius using the thermometer. You're going to change it to Kelvin. That's simply 273 plus the Celsius. You get the value in Kelvin. Then you're ready to do the calculations that were the whole point of the experiment. The first one is the experimental gas constant R. If you have these four values, pressure, which you just figured out in part 2, you have the volume of the gas that you just changed to liters, you have temperature, which you just solved right here in Kelvin, and N, moles of hydrogen gas, you got from the stoichiometry part of it. You plug all those in, and mathematically you could solve for N. So when you're solving for the experimental gas constant, you're trying to solve for N. So what you're going to do is, you're basically going to plug in your P, your V. We're solving for N. I'm sorry, we're not solving for N. We're solving for R. You're going to plug in your N. So you're going to plug in your N. R is what we're going to solve for, and then you're going to plug in your T. So you basically found these values during the lab in one form or another. Plug them in and you calculate your value. Remember, the actual value for R is 0.0821, which will allow you to calculate your percent error in your error section to see how close you got to the actual value. The last calculation you have to do, or second to last calculation you have to do, is the experimental molar volume of a gas. What we're going to do is we're going to use PV over P1V1 over T1 is equal to P2V2 over T2 to find the STP conditions using the combined gas law. So what you would do is you would take your P1 from your experiment, your gas pressure, your volume from the experiment, and the temperature from the experiment. You plug in those values. These are all from the experiment that you set up. You measure, we just figured out P, you just figured out V, and you just figured out T, so you take all those. Then you're basically going to solve for STP conditions. So what we're going to do is we're going to put STP as 1 atmosphere here. Make sure the units cancel. The temperature would be 273 degrees Kelvin. And you're going to solve for the volume, what the volume would be at STP. So when you set this up mathematically, you're going to set it up to solve for what the volume would be at STP. So you plug in all the values. Those are just known values for STP. Then you get your volume. You get your STP volume. You put that on the top of the fraction, and you divide by the moles of hydrogen gas. That's the molar volume of a gas. The molar volume of a gas should be 22.4 liters. In your case, because of lab error, measurement, things like that, and dissolving, making sure the magnesium dissolves completely, you're not going to be exactly at 22.4. So 6 to find the experimental volume of a gas at STP. You plug in this thing from your experiments, pressure, volume, temperature. This is STP, 1 atmosphere, 273 degrees. You solve for volume. You find the volume. That goes then. The last calculation is going to be this. To find the molar volume of a gas, you put volume at STP right here. Goes up there. The moles of hydrogen that you solved in the first problem. When you divide the volume at STP by moles, you should get 22.4 liters. The last step in your calculations is going to be calculating percent error. The theoretical value for R is 0.0821. The experimental volume for molar volume of a gas, or the value, should be 22.4. So then you would do your percent error calculations based on that. Look up the percent error calculations. It's going to be experimental minus actual divided by actual, absolute value times 100. And that's how you do that calculation.